Alright, so in this video, we're going to go over section 2.3 of our textbook, which talks about continuity. So informally, a function is said to be continuous over a certain interval if its graph over that interval can be drawn without removing your pen from your paper when drawing it. So if we were to look at these three graphs here, let's first look at figure A. If we were to draw the graph of our function x plus 2, we see that we can draw this graph over this interval without lifting up our pencil. So this figure A is said to be continuous for all x. Now if we were to look at figure B here, so our function is this g of x, when we're drawing it, we actually do have to lift up our pencil because this value, so g of 2, is not defined. So we would have to draw this, lift up our pencil, and continue drawing. So this tells us that our function is going to be discontinuous at x equals 2, but it will be continuous everywhere else. So essentially over any interval that does not include 2. Now for figure 1c, we have this graph here, we have this function. And so when we're drawing this, we see that we do have to lift up our pencil to continue drawing, and this tells us that our function is not defined at x equals 0, so it is discontinuous at x equals 0, but it will be continuous over any interval that does not include 0. So that's how we can look at a graph and determine continuity, but formally, here is our definition of continuity. So a function f is continuous at the point x equals c if the limit of our function as x approaches that point does exist. Additionally, our function at that point, our function value at that point also needs to exist. And lastly, the limit of our function as x gets closer to that point is going to be equal to our function value at that point. So a function will be continuous on some interval a, b, if it is continuous at each point on the interval. So if one or more of these three conditions fails, then the function is said to be discontinuous at that point. So we'll look at this problem here. We want to use the definition of continuity to discuss the continuity of this function whose graph is shown here. So what we'll do is we'll look at the limit of our function as we get closer and closer to these points here. As we can see, there's some sort of jumps, some things are undefined, so we're kind of just going to investigate and see what happens looking or using the definition of continuity here. So first, I'll look at the limit of our function as x approaches this point here. So that is -3. So as x approaches -3 from the left here, we see that our function value is 3 here. Similarly, if we were to approach -3 from the right here, we also get 3. So this tells us that the limit of our function as x approaches -3 from the right and from the left are equal and equal to 3, so our limit exists. However, if you were to look at the function value at -3, we have that it's undefined. So f of 3 does not exist. So this tells us that condition 2 fails in this case. And we have a discontinuity, I'm just going to abbreviate it that way, at x is equal to -3. All right, similarly, we're going to look at this point here, -1. What we'll do is we'll look at the limit of our function as x approaches -1 from the left. So we see as we approach -1 from the left, our limit is about 1 here. And if we were to approach -1 from the right, we're getting closer and closer to 2. So this tells us already that our limit does not exist because our one-sided limits are not equal. So we immediately violate or fail this first condition, our limit does not exist. So we have a discontinuity at x equals -1. All right, let's look at the next one. We want to look at the limit of our function. This is 2, as x approaches 2. And we can see easily that if we approach 2 from the left and from the right, we're getting closer and closer to 5. So our two-sided limit of our function as x approaches 2 is 5. And so our limit does exist. Then we'll check our second condition. So f of 2 here. So we see that at this value 2, our function value is 4. But since the limit of our function as x approaches 2 is not equal to the value of our function at 2, we have a discontinuity at that number. And this is because we're violating or failing the third condition here. All right, and then lastly, we'll look at the limit of our function as we get closer and closer to 4 here. So look at 4 from the left first. You can easily see that as we get closer and closer to 4 from the left, we're getting closer and closer to 4 here. And if we look at our limit from the right, we see that our function is getting closer and closer to 2. So our limit does not exist because our one-sided limits are not equal. So we have a discontinuity at x equals 4. All right, so that is how we'd use the definition of continuity to look at a function whose graph is given here. Next, we'll use the definition of continuity to discuss continuity of functions at given points. So first we'll look at A here. I'll put it here, there's not too much room. So we're given this function, f of x is equal to x plus 1, and we want to look at the continuity at that given point, which is x is equal to 1. So we'll just look at our conditions. We want to look at the limit as x gets closer to that point. So plugging that in, we get 2. And then plugging the function, or plugging x equals 1 into our function gives us 2 as well. So our limit of our function as x approaches 1 is the same as the function value. Oh, sorry. This should be f of 1. When we plug 1 into our function, we get 2. And so this tells us that our function is continuous at x equals 1. All right, and that's because we satisfied the 3 conditions here. The limit exists, the function value exists, and they are equal. All right, let's look at B. So we're gonna do the same thing. We're gonna look at the limit of our function here as x approaches 1. So we'll plug 1 into our function, and we end up with 0 over 0. So our function is undefined and therefore discontinuous at x equals 1. All right, and then lastly, we'll look at C here. So again, we're going to look at the limit of our function as x approaches. We're going to look at 0 and 2. So I'll do 2 first. And again, plugging this into our function, we're going to plug in a 2 here and a 2 there. We get 0 over 0. So our function is undefined and discontinuous at x equals 2. Now let's look at the limit of our function as x gets closer and closer to 0. So plugging this into our function, we get negative 2 on the top and 2 on the bottom because we have our absolute values. This is equal to negative 1. Now notice if we were to plug negative 1 into our function, so we plug in negative 1 here and negative 1 there. Oh, sorry. We're looking at x equals 0. So if we were to plug in 0 here and 0 there, we would get negative 1. So this tells us that our function value at x equals 0 is equal to the limit of our function as x gets closer and closer to 0. And therefore, our function is continuous at x equals 0. All right. So in this little blurb here, we can also talk about one-sided continuity, just how we did about one-sided limits. So a function could be continuous on the right at x equals c if the limit of our function as x approaches c from the right is equal to f of c. And similarly, if we were to look at the continuity on the left as x gets closer and closer to c from the left. All right, now a function is continuous on the closed interval a, b if it is continuous on the open interval and is continuous both on the right at a and on the left at b. Now here are some general continuity properties. If two functions are continuous on the same interval, then their sum, difference, product, and quotient are continuous on the same interval as well, except for values of x that make the denominator 0. We also have this theorem here, theorem 1. I'm not going to state each property, but essentially these properties in this theorem here allows us to determine intervals of continuity without having to look at graphs or use the three definitions of, or the three conditions of continuity that we discussed here. So we'll illustrate this with an example. So here we're told to use theorem 1 and the general properties of continuity to determine where each function is continuous. So for part A, for example, we have this polynomial function here. And looking at this theorem, theorem 1, part C of this theorem tells us that a polynomial function is continuous for all values of x. So this tells us that our polynomial is continuous everywhere. All right, so pretty simple. We can just use our theorem. We don't have to, so this would be by theorem 1, part C. So this way we don't have to look at the graph or use the definition of continuity and check all three of those conditions. So looking at part B, we have a rational function here. If we go back to theorem 1, part D, it tells us that a rational function is continuous for all x, except those values that make the denominator 0. So this tells us that f of x will be discontinuous at x is equal to -1 and x is equal to 4. Because if we were to plug these values into our denominator here, it would make the denominator 0. Okay? So it'll be continuous everywhere except for these two values. All right, now part C, we have this radical here. And we're told by part F of our theorem that if we have this square root function for an even positive integer here, it'll be continuous everywhere. F of x is continuous and non-negative. So we have this square root here, so our end value is 2 and therefore even. So that means our function is going to be continuous everywhere that f of x is continuous and non-negative. And so we know, I'll say f of x will be continuous on the interval 4 to infinity. Because if we plug in 4 for x, we just get the square root of 0. But anything smaller than that will give a negative number in our square root. And so this is the interval that our function will be continuous. And then part D, we have the third root here. And then part E of our theorem tells us that if we have this radical here for a odd positive integer, then our function is going to be continuous everywhere. So f of x is going to be continuous everywhere. Because our function under our radical, the x cubed plus 1, is continuous everywhere. All right, so now we'll look at solving inequalities using continuity properties. And we'll do this using theorem 2. So we're told if f is continuous on some interval, and it's not equal to 0 for all x in that interval, then either f of x is greater than 0 for all x within this interval, or it's less than 0 for all x in this interval. So in general, if f is continuous and f is not equal to 0 on our interval, then f of x cannot change sign on that interval. So if f of x were to change sign, this would violate the fact that f of x cannot equal to 0. So visually, we can look at this by looking at our x and y axis. So this is f of x and this is x here. And so we know that this is our positive region, so this is where f of x has positive values, and this is where f of x has negative values. So for f of x to change sign, so go from our positive to our negative region, at some point we would have to cross the x-axis. So in this case, f of x would be 0, and then this would violate theorem 2, the fact that f of x cannot equal 0. All right, so what we'll do is we will solve this inequality here. We have x squared minus 1 over x minus 3, and we want to figure out where this function is less than 0. So we'll use theorem 1 to do this, and we will first start with finding where our function f of x is discontinuous and where it's equal to 0. So we have a rational function here, x squared minus 1 over x minus 3, so we know that our function will be discontinuous when our denominator is 0. So discontinuous when x minus 3 is equal to 0, so when x is equal to 3. We also have that our function will be equal to 0 when our numerator is equal to 0, so when x squared minus 1 is equal to 0, or I'll write it as this. Our function is equal to 0 when x squared minus 1 is equal to 0, and this happens when x is equal to negative 1 and positive 1. Okay, so these numbers here are called our partition numbers, and we're essentially breaking up our number line into intervals based off of these partition numbers. So that leads us to our second step here, determine our intervals. So if we have our real number line, like this here, and we have negative infinity here, infinity here, so this is negative 1, 0, 1, and let's say this is 3. We're breaking up our number line into intervals based off of our partition numbers here. So our first interval is going to be negative infinity all the way to negative 1, so this region here. Then our second interval is going to be this region here between negative 1 and 1. These are our partition numbers here. Our next one is going to be from 1 to 3. And then our last interval will be from 3 to infinity. All right, so now we have broken up our number line into these intervals. We know that within these intervals, our function f of x will be continuous and it will not be equal to 0, right? Because we determined from this here that only at -1, 1, and 3 will our function either be discontinuous or equal to 0. So everything in between is fair game. We are continuous there and f of x is not equal to 0. By that logic, we can now use theorem 2 to determine the sign of our function, right? Because like I said, in these intervals here, our function is continuous and not equal to 0. So this tells us for any x in these intervals, our function will either be positive or negative. So this tells me that I can pick any number within these intervals to determine the sign of our function. So I'm going to pick some easy numbers. So I'm going to pick -2 there, zeros in this one, 2's in this one, and 4's in this one. And so these are called test numbers. So this brings us to the third part. Use test numbers to determine the sign of f of x. So I'll go to the next page here. So using our test numbers, we're going to plug them into our function. So f of -2, plugging it into here, we get -2 squared, which is 4 minus 1, so we get 3 on the top, and then we get -2 minus 3, so -5 on the bottom. And we don't actually need to find the exact number. All we're looking at here is the sign. So this will be negative. Plugging 0 into our function, we will get -1 over -3. So this is equal to just 1/3, so it's positive. And then plugging 2 into our function, we will get 3 over -1, which is just -3. And so our function is negative in that region. And then lastly, we're going to look at f of 4, which is, we got 16 minus 1. Okay, so we got 15 over 1, which is just 15. So our function is positive in this region. All right, so now we can construct what's called a sign chart. And it looks like the following. We have our function here, and we're breaking it up into our intervals. So we have -infinity to -1, -1 to 1, 1 to 3, and 3 to infinity. And so what we're doing here is just organizing what the sign of our function is in these intervals. So when we took a test number in this interval, we found that our function was negative. Then when we took a test number in this interval, -1 to 1, we found our function was positive. And here we found negative, and then in here we found that it was positive. So that's how you would construct a sign chart here. And again, this is just because of theorem 2. It tells us that in these intervals where our function is continuous and not equal to 0, our sign will not change. So from -infinity to 1, it'll always be negative. From -1 to 1, always positive, and so on. Now, if you remember, what we wanted to do is solve this inequality. So we wanted to figure out when our function would be less than 0, so when our function would be negative. So to answer this question, f of x will be less than 0 in this region here and this region here. So when x is less than -1 and when x is in between 1 and 3. And then in interval notation, this can be written as -infinity to -1 union 1 to 3. All right. Now this brings us to this definition here. As we saw in the last example, A real number x is a partition number for a function f if f is discontinuous at x or equal to 0 at x. So that's what we found here. Our 3, -1, and 1 were our partition numbers. And so these, I'll write this out. Our partition numbers will determine the open intervals on which our function does not change sign. All right, and then this here is our procedure for constructing sign charts here. This is the procedure we followed to find our sign chart in this last example. Next is look at another example of this. We're given this problem here. So a bakery estimates its annual profits from raisin bread to be given by this function here, p of x. And we want to figure out for which values of x does the bakery make a profit selling raisin bread. So in other words, if p of x represents the profit, we want to figure out, so we want to determine when our profit will be greater than 0, or our p of x will be greater than 0. This will determine when we'll make a profit. So first step is we want to find the partition numbers of f. So when f is, or in our case, p of x is discontinuous or equal to 0. So the first thing to note here is that p of x is a polynomial. And then by theorem 1 at the beginning of this section, this tells us that it's continuous everywhere. So that won't give us any partition numbers, but we can find when p of x will be equal to 0. And we'll do this by factoring. So we have p of x, we want to figure out when it's equal to 0. So we need two numbers that'll multiply to be 6,000 and add to be 7. But it's not as complicated as we think because we have this out here out front. And remember, this value is the same thing as 1 over 1,000. So we'll use that. And we know we have x squared. And we know that we have two numbers that need to be multiplied to be 6,000. So I'll say 6,000 and 1,000. And then we also have this negative 0.01 as our coefficient for x squared. So we'll still have this on the outside. And then this tells me when we're multiplying everything out that we will get a minus 6,000 and a positive 7 if these are both negative here. All right. So this tells us that p of x will equal 0 when x is equal to 1,000 and 6,000. Now these are our partition numbers, and this will help us determine our open intervals. So our first interval is going to be negative infinity up to 1,000. Our next one will be the interval between 1,000 and 6,000. And then our last one is going to be from 6,000 to infinity. All right. So now what we want to do is find some test numbers within these intervals. And again, we can pick super easy numbers because theorem 2 tells us that our function will not change sign within these intervals. It's only changing signs when we're outside of these intervals. So for this one, I'm going to pick 0. For this one, I'm going to pick 2,000. And for this one, I'll pick 10,000. All right. So plugging 0 into our function, we will get negative 6,000. So this is a negative number. Plugging 2,000 into our function here, we will get 2,000 squared, which is 4,000, times this will be negative 4. Then we have 7 times 2,000, which will be 14,000. And then we have a minus 6,000. Now we don't need to know this actual number. All we need to know is that 14,000 minus 6,000 minus 4 is going to be some positive number. Because all we care about is the sign of the function here. And then lastly, we'll look at 10,000. Plugging that in, we get 10,000 squared times negative 0.01. So this will be negative 100,000. Then we have 7 times 10,000, 70,000 minus 6,000. And again, we have negative 100,000 plus 70,000. That's still going to be a negative number. And then we're taking away even more. So this will still be a negative number. And so we can construct our sign chart. So we have our function. A little straighter. And then we have our intervals. All right, and then our test numbers told us that in our interval negative infinity to 1,000, our function will be negative. The next interval, our function will be positive, and our last interval, it'll be negative. All right, and then going back up to figure out, or to remind us what our actual question was, we want to figure out when p of x will be greater than 0. So in other words, when p of x will be positive. And our sign chart here tells us that p of x will be greater than 0 for x values within this interval. So x values in between 1,000 and 6,000. All right, so that's it for this video.